next or third problem in this practice exam, which is ultra-high molecular weight polyethylene nylon composite. So working with a composite material made of ultra-high molecular weight polyethylene, so UH, I'm just going to name that PE, and nylon. Young's modulus of nylon, so E of our nylon is going to be 2.7, which is also going to be our fiber, because that's larger, 2.7 GPa. Young's modulus of our PE is going to be modulus of our matrix because Young's modulus is smaller, so that is going to be approximately 0.8 GPa. And we could actually start to kind of write some of these values down. So our E of our fiber is equal to 2.7 times 10 to the 9th. Our E of our matrix is equal to 0.8 times 10 to the 9th. So let's write those values down. I'm working with a 25-75 composite mixture, so I know that the fraction of my fiber is going to be 0.25 because it's always a smaller value typically, and if our matrix is equal to 75. So I could write those values down, and then I can start to calculate some interesting or important parameters. So fraction of the fiber, 0.25, fraction of the matrix equals 0.75. And now I know if I want to look at the Young's modulus in the fiber direction, which I'm going to call the one direction, it is just going to be EF times FF plus E matrix times fraction of matrix. And in the transverse direction, pulling in the opposite direction of the fiber, it is just going to be this 1 divided by EF. Divided by, and actually, let's go ahead and look that value up from our previous lectures, lecture 14. So let's look all the way back to this expression for in the axial direction of the composite versus the fiber direction. So 1 over fraction of F, fraction of the fiber divided by E of F, plus fraction of matrix divided by E of matrix. There. And we can see, again, smaller Young's modulus makes sense. Stiffer in the direction that's along that fiber direction, not transverse. So we're going to come back to this because we're going to need to utilize this in just a second. So let's go ahead and look back at our practice exam. And we can see, okay, luckily in this first stress state, in the initial stress state, we're already pulling along this fiber direction. So I can see that my nu 1,2 is equal to 0.2. So let's go ahead and write some of these values down. So luckily I'm given nu 1,2 is equal to 0.2. That the normal stress parallel to the fibers, so i.e. in the sigma 1,1 direction, is equal to 58 megapascals. And that is positive because we're extending the material, so 58 times 6, and sig 2,2. I also know that the, excuse me. So parallel to the fibers, so it was, so parallel to the fibers was 10 megapascals, so 10 times 10 to the 6. Right here. So the normal stress parallel to the fibers was 10, while the stresses transverse to the fiber direction here was 58. And I also found, so transverse to 2 direction, I also found out that my gamma 1,2 is equal to 0.06. And I also know that essentially my epsilon 1,2 is going to be m1,2 divided by 2. But anyways, we'll get to that in just a little bit. So the shear modulus of the composite in this plane, so I need the G12. We'll see that in just a second. So let's go ahead. Excuse me, my pen is giving me a little bit of an issue here. There we go. So my G12 is equal to this 0.2 GPa. So let's go ahead and look at that value, or put those values in, not gamma 1,2, and G12 is equal to 0.2 times 10 to the 9th. All right, so it says first write out the full stress and strain vectors for this plane stress state. So what do I have left unknown? I need to then, effectively, I need to solve for what is 1,1, what is the strain in the 2,2, and what is my stress in the 1,2 direction. So again, I mentioned that we could be going back to this, but we have everything we need in here, except now we need to set up our S matrix. So my S is equal to 1 over E1. We already have that solved for, minus nu 2, 1 divided by E2, 0. This is my compliance matrix. So minus nu21, or 1, 2, excuse me, divided by E1, 1 divided by E2, 0. And then finally 0, 0, and 1 divided by G12. So I have actually an additional unknown here. What is nu21? Well, I know that this compliance matrix must be symmetric, so therefore I know that this is equal to this value right here. So in doing that, I could solve for nu21. So nu21 is equal to this. So that value right here. And I can now get my full numerical compliance matrix, just like that. So that's all we need now in order to kind of solve for the rest of this problem. So I'm going to set up an expression that looks like this and solve. I need my E11, I don't know, E22, I don't know, but I do know my gamma 12. And that is going to be equal to when S dots with sig11, which I know, sig22, sig12, which I don't know. So 3 equations, 3 unknowns. So solve for E11, E22, sig12. And that's it. Those are my values right here. So I could set those. E11 is equal to this. My E22 is equal to this. Right here. And then finally my sig12 is equal to this. There we go. Make sure that sig12 looks fine. All right. So those are my stresses in that initial, what the problem was asking for. The full stress and strain vectors for this plane stress state in that initial system. So now it says, turns out in our application, the fibers must be oriented 45 degrees from the 1 and 2 axis as shown below. So we need to rotate our system and apply that same stress. So we need to figure out, okay, what is going to be the new stress, strain and stress vectors for our composite material? Well, let's go ahead and solve this in a number of different ways. So we're basically taking our system, we're rotating it, and we're seeing, okay, what's going to be now the stress in that kind of that new coordinate system. You could kind of imagine it either looking kind of like this new composite stress state, or if we're able to, again, it's just this idea of rotating the coordinate system. So instead, if we're looking at a plane that's oriented like 45 degrees along this direction. So if we take this initial coordinate system, basically our 1 and 2 here, so 1 and 2, and we want to rotate to this 1' and 2' direction right here. So we're just kind of doing this rotation. It's effectively, that's what's going on here. And we know that that orientation is 45 degrees. So let's go ahead and solve for that problem. I can do it in multiple ways. So now I'm going to say stress old, which is going to be my sig11, sig22, sig12. And I'm going to also define my strain old, which is going to be E11, E22, E12, actually gamma 12. So there's several ways that I could solve for this problem. So let's do it first. For example, I can just simply do this. So stress T dot stress old. I want to convert to new coordinate system. Let's define what T is. That'll be very helpful because we're going to essentially use these series of equations here. So if I want to find the coordinate system in my new system, or my stress values in my new coordinate system, I'm just going to do T dot stress old slash dot theta goes to 45 degrees. That would be my stress. I can do the same thing. You can see kind of these values for here for strain. R dot T dot inverse R dot strain old slash dot theta goes to 45. I could get these same values here. I could also do a little bit of a trick. So I can get if I wanted the tensorial definition of my strains, I could do my, let's see, actually I'd have to kind of do this little trick. So strain old, I'm going to call this my tensor notation. Because if I put everything in tensor notation, I'll actually be able to get T dot strain old tensor slash dot theta goes to 45. And you'll notice, look, it's exactly the same from this answer, but off by a factor of 2 here. And the only reason is because, again, this is our engineering definition. So if I divided this, so divide this by 2, we'll get this exact same answer. So there are multiple ways you can kind of get to this expression, or you could even do this kind of nastier expression, or not nasty, but you can kind of confirm your answer. So I'm going to call this my new stress, except I'm going to actually make it a variable. So I could use this r dot t dot inverse r dot s dot inverse of t dot my new stress and slash dot when theta goes to 45 degrees. And let's see, same, same, same. So you see our two equations are equivalent. So multiple ways, again, you could double check your answers, but those will be the stresses and strains in our new coordinate system. Excellent. So final question, or actually, let's see if it's the final question. Well, thankfully, it's the final question. Final question, what rotation gives us our principal stress state from this composite? And what rotation does this correspond to for our old stress state? Well, if I want to look at what's the principal stress state for this composite, I could do it multiple ways. So I could do, if I want to actually solve this problem, what rotation gives us our principal stress state for this composite? What rotation does this correspond to for our old stress state? An easy way to solve this problem is to just look at your stress old. So in my old, before I'm looking at that plane of interest, I could just do t dot stress old, and I want to look at, again, this will give me, if I kind of solve for some values, it'll give, like, let's say theta goes to 45, for example. I need my principal stress state will be when my shear stresses are all equal to 0. So I can go ahead and solve for when does this third value, my shear stress, when is it equal to 0? What value of theta? And you're going to see several different answers pop up because, again, depending on the circular symmetry of your Mohr circle, these different rotations. So you can see this angle of 13, 76. Again, it's all kind of circular symmetry that kind of depends on these different values. But that would be the rotation from the old stress state as well. You can also solve this from the perspective of the new stress state. So stress new. Where did I call it my new stress? And solve for the values. Again, you see the angles are different, but again, because we're in a different, we're in a different state on our Mohr circle. So our principal stress state will remain the same, but you'll see that these values, again, you have some Mohr circle, you have all these different points here, these different vectors or, stress states that can possibly occur. So that's why you kind of see those different angles that can pop up. So, but that's essentially how you'd solve for this problem. So any of these angles would be correct. But I think the easiest way would be, again, because it's asking you for the rotation from our old stress state. So just use the old stresses and then you'll be able to solve for that. All right, excellent. That's your composite problem. Next problem will be into our kind of dynamic mechanical testing, and that'll be more of a firm problem, more quantitative, which I know everyone loves, and a lot of polymer thermodynamic and intuitions. Excellent. I'll see you all on the next video. Thanks.